Hey guys, so today's video is going to be on alternating series. Now I assume you already know about alternating series, so you're familiar with them because I don't want this video to be too long. But basically this is what an alternating series is. It's -1 raised to the index's power times some, function with something to do with the index, right? So basically, I want to talk about the notation first. So the notation, I'm saying it's n greater than or equal to 1. That technically means n equals 1 to infinity. I'm just writing it this way because I think it looks a little better, a little cleaner. And there could technically be some endpoint, like n equals 1 to 50, as long as you go like quite some distance, but I'm just going to assume that everything goes to infinity for simplicity. So, why is this called an alternating series? Basically, all you do is, we'll just plug in your n values starting at 1. And you'll notice a pattern. So -1 to the first power times a sub 1. And your a sub 1, a sub 2, those don't really matter, plus a -1 squared, a sub 2 plus -1 cubed, a sub 3, and then you keep adding. I'm just going to go, -1 to the fourth. -1 to the fourth, a sub 4, and then you just keep adding some more terms, basically. So what happens here? -1 to the first power is just -1, and we apply that to the a sub 1, okay? So then -1 squared is a positive, so that's just going to be a sub 2. -1 cubed is negative, so minus a sub 3, and then plus a sub 4, and so on. So then you'll have a minus for the next term. You could also shift this over by starting at 0, because -1 to the 0 is 1, so that'll be a positive, negative, positive, negative. Or you could start at 2, or really any even number, and you'll start with a positive here, and then a negative. But if you start with an odd number, you'll start with a negative, and continue going with the positive, just for this basic reason. So, you have some freedom with these alternating series, and so the reason why it's called alternating is because the signs alternate. Minus, plus, minus, plus. But like, what if you wanted to do like a minus, minus, plus, plus, minus, minus, plus, plus, and that's what we're going to be doing in this video, because I think this is a very interesting idea, and so, yeah, we're going to be using some cool things, so let's get straight into it. So what do we want? Let me write, yeah, so what we want is something like, we'll have, so a negative and a negative and a positive, positive. Well, how are we going to get that? Well, I mean, we could be like 1, 3, 5, like 1, 3, 4, 6, like having it kind of like that with the exponents, but that's kind of random and it doesn't really work well. So what if we had like the same number for here, and then the same number for those two, so like it would be a 1, 1, 2, 2, 3, 3, So, I mean, we could try that. So what we want is some, we'll say like some terms b, or actually let's use f. So we want f sub 1, or actually, no. So these functions aren't the same really, basically. So we're gonna, let's see. So we want a function such that, first power, second power, second power. So let's say our first index, we can denote that again as f1. This is equal to 1. f2 is also equal to 1. f3 is equal to 2. f4 is also equal to 2. f5 is equal to 3. f6 is equal to 3, and so on. And of course we can shift it over by saying this is 0, 1, 2, but that doesn't really matter as long as it just alternates in some way. So we want like some sort of expression, some like f sub n value that kind of just does this, and it makes it like that. So how do we do this? Well, if you know about the floor function and the ceiling function, those might come to mind. I assume you know about those. I have a link in the description of I think a short video that I made for the functions. So basically, let's see. So the floor of x is just the greatest, or like it's like, I like to refer to it as like rounding down. So floor of, 0.5 is equal to 0, but the ceiling of 0.5 is equal to 1. So I have a video on that, explaining that more in detail there. So yeah, basically you're rounding down, rounding up. So what if we had, like, you know, this term is like our first term, we could say like our f1. So let me just draw a line, draw a better line. Okay, there we go. We can say our f1 can be equal to 1. Our f1 is just, you know, hold on, what am I doing here? Well, we can have our first term, so what if we take the floor of all those functions, basically? So we can, I'll just say g1. So g1 is equal to 1. g2 is equal to 3 halves. g3 is equal to 2. g4 is equal to 5 halves, because 2 is 4 halves. g5 is 3, and then g6 is 7 halves. So what is this doing? If we take the floor of all of these, floor of an integer is the integer itself, so this is 1, this is also 1, because floor of 1.5 is going to be 1, 2, 2, 3, 3. So basically, if we take the floor of our g's, that's going to give us our f's. So we can make the connection that the floor of g sub, I don't know, k, or actually I might use k later. Let's say g sub m, floor of g sub m is equal to f sub m. And this is what we want. We want something where we raise it, and we're realizing, like, if we just, these are like our exponents, so if we raise this to the f sub m power, basically what we're doing is we're raising it to the floor of g sub m. But what is g sub m? Well, we can look at these integers, these integer values, as what I was saying earlier. So this is 2 over 2, that's 1. This is 4 over 2, and this is 6 over 2, right? Because 2 over 2 is 1, 4 over 2 is 2, and 6 over 2 is 3. So we can see that there's a connection. All of these have a denominator of 2, and we're increasing by 1. So it's like there's a pattern. There's 2, 3, 4, 5, 6, 7, and so on. Again, if we shift it over by, like, starting at 0, we'd have a 0 over 1, 0 over 2, and 1 over 2, which would shift this to start with a positive. So basically what we're going to do is, we know our g sub m's are in some form of, like, let's say capital M over 2, where m is some integer. So the floor of that, so the floor of g sub m is going to be the floor of m over 2, capital M over 2, I mean, and that's just going to be equal to, well, it's basically what we are, I guess we can't really simplify this one, but, it's the greatest integer that's going to work for this, so it's going to be 1, it's going to be also 1, 2, 2, 3, 3. So this is what we got to plug into up there, because we can't simplify this anymore. So we're going to plug this into our exponent in our sum to see, would this work? Because you could think of, like, oh, what if we had the I power? That's not going to work. You can try it out, but that's not going to work. So it looks like if we wanted to generalize it, let me make sure I'm actually writing. Let's start with k. Yeah, let's do k is greater than or equal to 1. We could start at 0, or really anything if we wanted, of -1, but not raised to the n power, but to the, it's going to be k over 2, floor of k over 2. And so then we're going to multiply by, I guess we could do b sub k. So let's just try to see what we get. So we get -1 to the floor of 1 over 2. That's our first k value. Hold on. So -1 to the floor of 1/2 is 0. Okay, so I'm starting. Okay, actually, this is something also you should note. You should start at whatever the denominator is, so that it's kind of like it's like shifted over, and I'll show you why that's more important later. So we'll just start at 2. right now it's kind of arbitrary, but we're starting at 2. So negative 1 to the 2 over 2, that's 1, floor of 1 is just 1. So negative 1 to the first power, so negative b sub k, okay, or actually b sub 1, or b sub 2, because that's our technically first term. So then what we're going to do is negative 1 to the, so floor of 3 over 2 is going to still be 1, so we're going to get minus b sub 3, okay. Negative 1 to the, so floor of 4 over 2, which is floor of 2, which is 2, so negative 1 squared, is going to give us a positive b to the 4th. 5 over 2, floor of that is also 4, so this is also going to be a positive b over 5, or b sub 5. And you can see that the pattern is going to continue as we go down the list and go on towards infinity. So you can see that the next one is going to be a minus b sub 6, minus b sub 7, and then we're going to just add b8, b9, and basically that's the pattern we're going to get. So that is specifically if we have the value of 2. If we're looking for, you know, a gap of, or groups of 2, you know. So up here we have groups of 1. Down here we have groups of 2. So what if we had groups of, I don't know, like, I guess we already used m, n, and k. What if we had groups of, I don't know, some other thing? Let's say groups of z, or, you know, why not? So so here, let me point out that this is groups of 1. So groups of 1. Down here we have let me see, groups of 2, and now we want groups of z. Groups of z. For z as some integer, of course, because, you know, we can't have like a half of a group of numbers. I don't know, it's just weird. Because we're dealing with sums here, it's going to be all, you know, integers. Natural numbers, actually, because it can't be negative, because it can't have a negative number of terms. It's weird. So we divided by 2, but why did we divide by 2? I just kind of like brought that up, and it did work. But why did I choose 1/2? Well, you could guess 1/2. 1/2 is probably the first thing you would guess. But what if you start with like a third? You know, or what if your denominator was 3? Well, then you can check these floor patterns. Floor patterns, that sounds weird. Floor of 0 over 3 is 0. Floor of 1 over 3 is also 0. Floor of 2 over 3 is 0. So that's a group of 3 right there. If you had groups of 4, you know, if your denominator was 4, then floor of 0 over 4, 1 over 4, 2 over 4, and 3 over 4, that's all 0. So your groups of z is going to have a denominator of z, basically. So we can actually really just generalize this now. So actually I don't like z, because z is a weird index. We can use the index I. So we're starting at I greater than or equal to oh wait, I is not actually our index. Yeah, no. Okay, I guess z is okay. So z. So I, it will be our index here, and it's greater than or equal to z. And we have -1, as always, to the floor of what? Well, of course, we're going to have our I value up top. I not being the square root of -1, this is just our index, divided by z. That's what we just determined, you know, because if we want groups of z, we have to have the denominator with z, so that's what we have up there. And then times our arbitrary, we can say a function f sub I, because that's what we're dealing with. Okay, so let me just kind of make this a little straighter here. There we go. Okay, so we have our expression here. So why did I choose z instead of like 0 or 1? Because I talked about the denominator down here, and essentially, was there a fly in my head? That was weird. Essentially, the reason why you start there is because if you kind of had, how do I explain this? If you start at that term, so let's say our z was like 4. So if you start at the 4, then you're gonna have, you know, k is starting at 4, so you're gonna have the first k is 4 over 4, because it's k over z, and if k starts at z, then the first one is gonna be 4 over 4, which is 1. So that's if you want to start with a negative number. So we can say this is start with a negative, okay? I'm just going to write it like that. Now if you want to start with a positive, we'll say j, and I'll leave that blank for now, -1 to the j over z, I'm just going to keep using z, of, we can say g sub j, actually. There you go. So what are we going to start with? If we want to start with an actual positive number, because that's a good place to start, you know. Well, how about 0? Because 0 over z, oh, I'm sorry, 0 over z, 0 over anything is going to be 0. The floor of the next number, and the next z numbers, is going to also be 0. And, you know, -1 to the 0 power is it's +1. So if you start with 0, you're going to get a +1 as the first one, and then everything's going to alternate after that. So here, you start with a positive. Now, there are other forms of this sum you can have, but they have to deal with the ceiling function. So you can have ceiling versions of these, and you're going to have to shift some things around and play around a little bit with them. So I'm going to leave that for you to do. So I can say we have like a homework, and if you're watching this bar, that's fantastic, because you can do these, you know. Find a ceiling representation of this alternating series, this thing we found here with the groups of z. I've used the floor function, and instead of the floor function, what if you had the ceiling function, which is this one? So basically, we can, you know, the ceiling would be like that. So how would you use that? So if you do have an answer, please leave it in the comments below. Yeah, so that's the alternating series video. We started with this idea of, you know, just having like a negative, a positive, a negative, a positive, or positive, negative, you know. And then we expanded to the idea, well, what if we had groups of 2? And then what if we had groups of z? So now, what if we had a different way of representing that? So yeah, that's what we did in this video, so hopefully you enjoyed. Thanks for watching, and I'll see you in the next video.